Today's lifestyles and environmental priorities call for efficient, high-performance industrial and commercial buildings which are quick and easy to build. They must be aesthetically pleasing, safe in construction and use, but they must also be functional units which operate with maximum efficiency and minimum running costs. These demands have been met by factory-engineered insulated cladding panels, the technology of which has advanced a great deal in the last decade. Today, the majority of quality industrial buildings are designed using the latest rigid urethane insulated panel systems. These panels satisfy the specifier's need for guaranteed thermal performance, the restriction of air leakage, reduction of capital costs, and efficient running costs, facts which are well supported by industry research studies. Rigid urethane panels are quality engineered in the factory to ISO 9002 standards and provide guaranteed performance on site with no cavities or open texture to assist moisture, the greatest degrader of cladding systems, nor open chimneys to encourage spread of flames. But what of their performance in fire? A key concern to specifiers, fire brigades, insurance companies, and building control officers alike. In recent years, there have been a succession of serious fires in large single-story buildings, primarily within the food processing sector. In the main, they have occurred within compartments enclosed by self-supporting panels or adjacent to lining panels, both utilizing polystyrene as the insulating core. Details on the panel systems involved have generally been inadequately or misleadingly reported, which merely serves to confuse the issue. Rarely have fires originated in the external envelope. In fact, rigid urethane panels have performed exceptionally well over the past 30 years in cases of fire. By law, claddings have to meet the fire performance requirements set out in the building regulations, and often they must also satisfy specific client or insurance industry standards. Insulated panels have been tested and satisfy these requirements. However, given the misconceptions that still exist on the subject, EPIC commissioned an extensive series of large-scale tests covering all the commonly used cladding systems. We can now present the findings of these tests, which we believe will provide a clearer understanding of the reality behind the headlines and indicate how panels and traditional systems will actually perform in practice. The systems tested were multi-part built-up systems with glass fibre and rock fibre quilt, several panel systems with rigid urethane insulation, one panel system with high-density rock fibre insulation, and one panel system with polystyrene insulation. The cladding systems were built to the latest recommended industry guidelines, incorporating the most commonly used insulants, and with a thickness designed to achieve a thermal performance of 0.45 watts. All materials used were standard factory production, available to every roofing and cladding contractor, either supplied direct or obtained through main roofing stockists. Arup Fire were commissioned to undertake the studies, and Warrington Fire Research to carry out the comparative tests using the principles developed by the Loss Prevention Council for their standard 1181 building test for walls and ceilings. George Faller of Arup Fire describes the test method.
The LPC test procedure was chosen because it is a large-scale standard test and is often used in the building industry to judge the performance of wall and ceiling lining systems. We felt that this series of tests would give us a good indication of the comparative performance of different cladding systems as used in practice on conventional industrial buildings. The configuration and size of the test building enable us to use fire engineering analysis to predict the temperatures in the room during the test. The information gained by observing the temperature effects on the different panel systems is very useful for predicting the behavior of these systems when used on real buildings. The tests used a standard 35 kilogram timber crib placed in the corner of the room. The burning crib typically generated an average heat output of about 510 kilowatts over the period of the test, with a maximum heat output of about 1 megawatt.
The first series of 3 tests were conducted on standard multi-part built-up systems constructed using steel liner tray, tape vapor seal, insulation, breather membrane, and steel profiled outer sheet. The insulating material was 11 kilograms per cubic metre glass fibre, which is still used in the majority of standard cladding systems, and rock fibre quilt, which is used in most of the remainder of built-up systems. As expected, the performance of the built-up systems was generally satisfactory, the rock fibre quilt performing significantly better than the glass fibre. The components of the built-up systems are of non-combustible materials, but the binding agents and breather membranes provide some contribution to the fire load, which is demonstrated by the smoke emissions observed at the joints.
The components of the built-up system do not add significantly to the exotherm load in a fire, but it was found that they shrink significantly and that the self-adhesive securing pins failed at an early stage. The glass wool quilt shrank to less than 50% of its original thickness in places where the internal temperatures of about 500 degrees Celsius were recorded. The corresponding external facing temperature was in the order of 200 degrees Celsius. On the roof, where the internal ceiling temperature measured about 800 degrees Celsius, the insulation was reduced to a minimal thickness of vitrified glass, and the breather membrane burnt away where the panel joints opened up. The shrinkage was less in the case of the higher density mineral wool insulation, where the thickness of the roof was reduced to about 50% of its original thickness.
In summary, the built-up systems with mineral wool perform well. Glass fibre, which represents most of the current building stock, less so. Specifications with glass and rock fibre quilt are different from those using high-density rock fibre, and should not be confused with them, nor considered as a fire wall or barrier. Shrinkage between the facings will occur, and this is a point which should be recognised by firefighters, as flames from a significant developing internal fire can pass down the cavity, a fact which has been borne out in actual fires. The second group of tests was conducted on insulated panel systems. The panels used were all factory-produced units with the space between the facings completely filled with insulation, so that there are no gaps or cavities. The insulation autoadhesively bonds to the facings in the case of rigid urethane panels, or is secured with adhesive in the case of rock fibre or polystyrene cores. All panels were securely through-fixed to the support structure with steel fixings, as per current site practice. The polystyrene panels were secured in a rigid extruded aluminium frame. Secure through-fixings are one of the primary differences between external claddings and internal partitions, which are self-supporting, and this is the main reason why steel-faced panels do not collapse. The other main difference is in the joint detail. For external cladding panels, this is designed to be totally weather-tight and prevent air leakage. This tightness of the joint also strengthens the system and helps protect the insulating core from the main effects of a fire. The standard timber crib and arrangement developed by LPC was again used for all tests to allow direct comparisons to be made. George Faller describes the findings.
Up to 2 minutes into the test, there's little difference between the systems. The internal facings then start to buckle. This occurs to some extent for all panels, rock wool, rigid urethane and polystyrene, exposing the core insulant to flames at the joints. As the test progresses, the difference in performance becomes marked with varying degrees of contribution to the fire. Internal ceiling temperatures at this point are approaching 1000 degrees Celsius above the crib. High-density mineral wool and the fire-rated rigid urethane panels provide limited contribution to the fire. In the case of the fire-rated urethane system, this is partly due to the close internal and external stitching of the joints. Using these systems, the timber crib provided the bulk of the fire load. Their performance as regards stability, integrity and insulation is good. For other rigid urethane panel systems, there's a contribution of the core material to the fire within the smoke layer. But there was no flame spread observed in the core material between the linings, and the flames self-extinguished as the heat source from the crib died down.
With polystyrene cored panels, even with a fully interlocking joint, there was considerable contribution to the fire. The core melted and flowed out as flaming droplets. There was flame spread through the core, leading to eventual collapse of the unsecured facings. Final results show that complete structural integrity is maintained for the glass fibre built-up system, rigid urethane insulated panel, and rock fibre high-density insulated panel. There is, however, scorching of the plastic facing on the glass fibre system due to insulation breakdown. Internally, all facings buckled and showed loss of adhesion in the vicinity of the fire and required replacement. The low-density glass and rock fibre quilts showed severe shrinkage at 600 degrees centigrade and total loss over 800 degrees centigrade. General loss of insulation, burning of the breather membrane, and smoke channels down cavity voids. Inspection of the rigid urethane insulated panel showed that clearly there is no spread of flame down the core. Protective char is formed on the heated face. The insulation is affected to varying degrees and in some areas not at all. Fire-rated rigid urethane expands to fill the space behind the buckled liner, reducing the amount of exposed core to ingress of oxygen. The rock fibre high-density panel has a 4-hour fire resistance classification. It still showed buckling and adhesion loss of the internal facing directly adjacent to the crib, and damage to the core material to a depth of 25 millimeters due to burning adhesive and organic binding agents. As part of the fire engineering assessment, a test with rigid urethane cored panels was repeated with the addition of conventional sprinklers. Manual activation of the sprinklers was delayed until the crib fire was established.
As a result of the effect of the sprinklers, the smoke layer was cooled sufficiently to halt further decomposition of the core material, thereby stopping the production of combustible gases. This resulted in the extinguishing of the flames at the joints, and further damage to the panels was avoided, and over half the panels in this test remained unaffected. Smoke emissions too were significantly reduced.
What do the important findings of these tests demonstrate about panel performance? Polystyrene panels perform totally differently to all the rigid urethane systems, with total contribution of the insulant and fire spreading throughout the core, leading eventually to collapse. For the other panel systems, the detail of the panel joint and through fixing to structural steel are fundamental to their successful performance in fire. They perform well, integrity and security is maintained, and there is no collapse. Emissions vary between the systems. For panels satisfying insurance industry test standards, these are very low. All panels in the vicinity of a significant fire will be damaged and will need to be replaced to some extent, irrespective of the core or fire resistance classification. Distinction should be made between glass and mineral fibre quilt insulants, which shrink and create cavities, and high-density rock fibre, which is the basis of systems providing 4-hour fire resistance, albeit with a cost and weight penalty. It is now clear that, far from being cause for concern in relation to major fires, modern factory-insulated panels with fire-rated rigid urethane cores meet the building regulations and meet insurance company standards. Our tests show clearly the gulf between polystyrene-insulated systems and rigid urethane cored panels. They also serve to illustrate why urethane cored panels have been used successfully to clad buildings throughout Europe for over 30 years, and why they can be used with confidence to build secure, safe, and thermally efficient buildings for the 21st century.